It's a great honor to be able to introduce our last speaker of the session, which is Professor Kenichiro Itami. Ken and his center has been heavily involved in collaborative research with the CCHF, including extensive exchanges of students, and it's been a great global engagement with him. So it's a great pleasure to be able to introduce his talk. Every time I've heard Ken, he's actually a superb, energetic speaker. So it probably is good to be able to quieten him down a little bit, because he always gives incredibly exciting talks. And I'm sure even at this time, he's going to do the same. So the title of his talk is Creation of New Carbon Materials by CH Functionalization. Welcome, Ken.
Yes. Thank you, Hugh. Can you hear me?
I can hear you loud and clear.
Okay, that's great. Oh, so please, thank you very much for your invitations. So now Nagoya, can you go for the first slide? Is actually snowing, and so our building doesn't look as beautiful like this. But anyway, what I would like to talk is about the creation of new carbon materials by CH Functionalization. Next slide, please. I would like to start by thanking for CCHF for being a great partner with our center ITBM. So as many of you might know, we started exchanging researchers, mainly students and postdocs, between these two centers. And for the last 2 years, we were able to exchange over 10 students and postdocs. And amazingly, a lot of collaboration has resulted in the fruitful publication, as you will see here. So the next slide, please. So here I'd like to show the representative collaboration between our group and CCHF groups. What you see in the bottom left about the computational and experimental studies done by our group, as well as the Jamal Musas group at Emory University. So some time ago, we found that the certain nickel catalysts can activate the both CH bond of a heterocycle as well as the CO bond of phenol derivative to accomplish the interesting bi-aero coupling. And from the mechanistic study, we were able to uncover the new type of mechanism that is shown here. So what you see in the top right is the collaboration with Hugh Davis groups, and that we were able to achieve the rapid total synthesis of marine natural product called dictyrodendron A, shown there. What we are so delighted is the fact that two of our reactions, that is a rhodium catalyzed CHR relation developed in our group, as well as a rhodium carbonyl CH insertion reaction that are developed in Hugh's group, were able to use in the total synthesis. I'm particularly happy with this collaboration because Katie Shapiga, at the time, the grad student in Hughes Davis group, now in the minister, perhaps here in this talk, and also my previous student, Atsushi Yamaguchi, went back and forth between Emory and in Nagoya, and then finally accomplished this total synthesis. The last example in the bottom right is our nickel catalyzed new type of coupling reaction using ester as a leaving group. And what the Jamal's group did is uncover the interesting mechanism of CO bond and also the cysteine bond activation involved in this transformation. And then lots of other collaborations are ongoing, and I really hope that this two-center collaboration is going to continue. And what I would like to do today is to show you how these methodologies can have an impact in the material directions. Next slide, please. And particularly today, I would like to talk about nanocarbons, such as fullerenes or nanotubes or graphene. I don't think I need any introductions about how great these are. These are really, really exciting next generation materials. And what I would like to do is to contribute this field as a synthetic chemist and try to solve two big problems in this field. Next slide, please. The first, the problem that we wanted to answer is about the mixture problem. So as you might know, nanotubes or graphenes or graphene nanoribbons are interesting, but we can only have this as in a mixture of various structure by using the current method. So only logical way for making structurally uniform nanocarbon is to introduce the essence of organic chemistry. So what we're trying to do is to start from a small template, like a rings or polycyclic aromatic hydrocarbon, and try to grow them by atom precision. And we have another goal. Next slide, please. Try to discover or synthesis three-dimensional nanocarbon, which is experimentally largely unexplored. And hopefully we can do this by using the ZH activation chemistry. So what I'd like to start is to introduce you one of the methodology that we recently started to develop. Next slide, please. So the one that I would like to introduce is called APEX. It's an annulated pi extension reaction of aromatic compound that is perhaps could be a common strategy for making graphene-like compounds. So in this particular case, we're aiming at nanographenes. So the smallest template that we can start is polycyclic aromatic hydrocarbon, PAH, what you see in the left. In PAH, there are several specific regions, such as Bay region, K regions, or L region, which correspond to armchair or zigzag edge of the nanographenes. And what we would like to do is very simple. We wanted to achieve a region-selective annulated pi extension. Can you show next? Something like achieving like this. If we can have that, then we can achieve the growth some template nanographene synthesis, and also maybe we can use this for the late stage functionalization or fine tuning of the nanographene that we synthesize. But in organic synthesis, there are not many of these type of region selective apex reaction out there. Next slide, please. But after many experimentations, we were able to find the sort of the first generation apex reaction that it undergoes at the key region. Next slide, please. So the reaction turned out to be very simple. So all you have to do is to take a polycyclic aromatic hydrocarbon and treat that with the silicon bridge aromatics, which is going to behave as a pi extension reagent. And we apply cationic palladium-2 as a catalyst precursor, and we apply orthochlorinil as a unique oxidant and the ligand on palladium. And if you do that, you will see that the apex reaction product can be formed in a selective fashion at the key region. Next slide, please. Here I'd like to show the mechanism that is supported by theory. And the first step is a plate transmetallation to form the biphenyl palladium species. And that's followed by pi complexation of PAH at the K region, followed by Heck-like insertion, followed by second transmetallation, followed by reductive elimination and oxidation, forming PAH apex product, and the palladium 0 is going to be oxidized to palladium 2 by the action of orthochlorinil. The reason for the K region selectivity is because K region is most olefinic, and it turns out that this is very, very predictable. Next slide, please. And we found that this apex reaction is very versatile and predictable. So in the top example, when we apply this silicon bridge aromatics, then you can have a 2-to-1 apex reaction forming that nanographene in a region selective fashion. In the middle example, if you apply pyrene, which has 2 K regions, you can do the 2-to-1 apex reaction within a dibenzo cellulose to produce this type of nanographene. You can run this reaction in a gram scale without any problem. In the bottom example, if you apply bis pyrene, this has 4 key regions, so you can do the 1-to-4 apex reaction forming that kind of nanographene in a region selective fashion. Next slide, please. So we can use this type of apex methodology for the growth of nanocarbons. Next slide, please. For example, if you start from pyrene and then react with the yellow type of bis silicon bridge biphenyl, and 2-to-1 apex reaction took place to give the middle nanographene molecules in reasonable yield. But here in this molecule, there's 2 key regions still remaining, so that you can end cap this region by dibenzo cellulose again to do the 2-to-1 apex reactions. So in this particular case, we achieved the 4-time growth of pi system of parent pyrene molecule in only 2 steps. And this, I think, represents a nice example for catalyst-controlled regional selective CH activation growth. And the most advantageous features of this methodology is that we can directly use unfunctionalized PAH without any perfunctionalization. If I show this slides, someone would, will imagine that you can do much longer, nanographin synthesis. And indeed, this is possible. Next slide, please. So after many experimentation, we found that the polymerization is possible. So this is one example. What you see in the top left is the substrate, one specific substrate. And this substrate contains the red part, which is a K region, and the blue part is a silicon bridge aromatic. It's going to behave as a pi extended reagent. If you subject this substrate to the palladium autocolonial catalysis, you will have a polymer, and about the molecular weight is about 150,000, which is pretty long, and which means that we have a nanographin of 0.7 nanometer width, and the length is 135 nanometer, which is one of the longest. So what we're trying to do is now to visualize this and also do the structure activity relationships, property relationship study of this newly synthesized nanoribbon. Next slide, please. So during this study, we luckily, by accident, were able to access 3-dimensional nanocarbons having negative curvature. So actually, these 3-dimensional nanocarbons are kind of the interesting object that many theoreticians has been predicting, but largely unexplored experimentally. So this is one prediction from the very famous paper from Makke in Nature in 1991. So this is about the paper predicting how we can create diamond from graphite. So their group were able to put the sp2 hybridized carbon in a 3-dimensional periodic manner. So what you see in the blue is their answer. They predicted that you can actually align sp2 hybridized carbon on the Schwarz P surface, and this is what we now call Mackay crystal. It has not been synthesized yet, but it has predicted that this is harder than diamond. So obviously, this has a repeating unit. Next slide, please. As you can see here, as highlighted in orange and blue, you need a satellite negative curvature to realize this type of surface. And next slide, please. So if you zoom in more, you will realize that you need to have a PAH with a negative curvature, such as 7-circular or 8-circular. But the formation of such 7 or 8 member ring is not that easy for organic chemistry, and it has. I would like to mention that 8-circular in itself, or analogs, there has been only recently synthesized. Next slide, please. In 2013, we were able to access this type of negatively curved polycyclic aromatic hydrocarbons starting from quinolane. Quinolane is 1/3 structure of C60, and it looks like an aromatic bowl. And this is a collaboration with Larry Scott. And next slide, please. What my previous student did is that if we subject this quinolane to the action of our palladium fluoronyl catalysis and apply the excess amount of aerobroxine, all the CH bonds at the rim of the quinolane were activated and aerolyzed to afford very interesting deca-aerolytic quinolane. And then if we oxidize this with DDQ or iron chloride, what we found is we not only formed 6-member ring, but we found that the over-oxidation took place to form extensively in a ring-closed product that is C8830, consisting of 5 7-member ring. This is kind of amazing because this is all sp2 hybridized carbon who wants to be planar, and it contains extensive 7-member ring who does not want to be planar. So next slide, please. And then we uncovered from the extra-crystal structure analysis that this is all sp2 hybridized carbon, but rosy work, having both positive and negative curvatures. So, so we named this as a warp nanographics. So next slide, please. So I'll skip about the properties, but I mean, there was a one question, how does 7-member ring were formed? So this is one example. You start from compound 2, and upon oxidation, we're forming the compound 1 at the end. We were initially assuming that a 6-member ring formation took place first to form compound 3, and then thereafter 7-member ring formation took place, but we never observed compound 3. So we start reducing the number of DDQ, and next slide, please. What we found is not the compound 3, but the compound 4 and 5. And these are the compound that is already forming the 7-member ring, but have some non-formed 6-member ring. So these are the pre-warp nanographing, but we identified that the 7-member ring formation can be faster if you have a substructure highlighted in yellow. So this is something that we found. And these are interesting molecule in its own right. Next slide, please. Because you can really control the pi stacking, actually. So pi stacking, the stacking is critically important for device or material application. And what we saw in the previous warp nanographing in the right is not the extensive pi extension, but if you reduce that into 1 7-member ring, it's even less. What we found in the middle is that if you have 3 7-member ring, it's really, really nicely pi stacking. So currently, by knowing this, now we're making the middle part of analogs extensively toward device applications. So next slide, please. So although I didn't tell much about warp nanographing, but this is kind of the summary slides. So clearly, this is a new form of nanocarbons. It's a grossly warped and 3-dimensional, and I didn't tell you, but this is a chiral structure. And the reason of extensive negative curvature is because we have an extensive 7-member ring. Rapid synthesis is another advantage. It takes only 2 steps from commercially available pentalene using our CH activation. And then actually, this is not a black powder like a nanographene, other graphenes. It's a very stable and yellow powder, as you will see in the picture. And most striking feature is its solubility, perhaps. Because of its warp structure, it has a very low intermolecular interaction. Therefore, it's very soluble to common organic solvent. Believe it or not, the cubital analog is even soluble to hexane. This is really amazing. And then it has a reasonable absorption and green fluorescence according to this warp structure, and also the relatively large homolumo gap. And also, unlike fullerene or graphene, it has both reversible oxidation and reduction possible. So this is something that it may be very unique electronically for these nanographenes. So next slide, please. So after this discovery, we started to explore making a number of different types of 3-dimensional curved nanocarbons. What you see in the left is a super warp nanographene consisting of 260 carbons. And the Kenta was able to make this in a 4-step from pentalene by CH activation. We're having a hard time in structure identification, but we are thinking that we are really having these molecules. What you see in the right is the pi extended double helice made by Takao, and he made this in a 2-step from naphthalene by CH activation, or platinum polarial catalysis. And an interesting thing is that we were able to see the 3-dimensional network of pi stacking of this molecule, which is we were hoping to be able to apply for the materials. So next slide, please. So what I show you is that in addition to 6-member ring, 7-member ring are interesting. These heptagon creates negative curvature and a new form of carbons. Another interesting thing is that the 5-member ring is also interesting. The pentagon also creates unique structure, in particular creating spins and radicals. So next slide, please. The example that I would like to show you today is about this Dibenzo pentalene having a 6-5-5-6 ring fuse system. This is apparently having a 6 pi electron system, which is an anti-aromatic, and thereby having an amphiphilic redox behavior. What you see in the right is a pi extended analogs. It can be used for the key component for all FET. And then, but the synthesis is not that easy. But recently we discovered that this very easy, simple step synthesis is going to be possible by palladium orthocolloidal catalyzed CH annihilation reactions. All you have to do is to take the diaryl acetylene and treat it with a palladium orthocolloidal catalyst. What they do is the ortho position is selectively activated and it undergoes sequential insertion process and cyclization, forming this type of arylated dibenzo pentalene. So this has been already published 3 years ago. So if you're interested, please take out this paper. Next slide, please. What Takehisa found is that you can actually extend even more, and this is a collaboration with Mike Haley in Oregon. And so if you start from, for example, like fluorinol containing alkyne, which shown in the top and middle, you can do the CCH annihilation reactions, forming the 8 fused ring system that you have shown here. Dicarbonyl compound. Dicarbonyl groups can be arylated with aryl lithium, and then the resulting diol can be subjected to the divalent tin chloride to force the aromatization, dihydration, to form the fully conjugated system that is you see in the bottom left. The structure has been confirmed by the X-ray, and we found that this molecule have a spins. So I'm not going for detail, but this has a spin as well. Can you go for the next? So in addition to this monoalkyne, if we apply the alkyne, we'll see in the middle left, you can actually access 13 fused ring system by the 2-to-1 coupling reaction with the monoalkyne and dialkyne. If you do the 2 + 2 + 2 type of annihilation, you have an 18 fused ring system. This is amazingly elongated structure that people have never been synthesized. And also we were able to uncover that there's an open shell radical character of these molecules. Of course, the structure determination seems to be very difficult, but I mean, it's clear that CH activation really opened up generating this new type of carbon-based molecules. So next slide, please. So I'm sorry that I didn't extensively explain about the mechanism, but I hope I was able to convince you the power of CHF activation and catalysis for generating previously untapped structures related with the nanocarbon. And we hope that we were able to establish the new field of molecular nanocarbon science powered by synthesis, catalysis, and CH activation. Next slide, please. So if you wanted to look or learn a little more about this issue, so please take a look at our most recent review, appeared in last week in the Nature Review Materials in the first issue, entitled Structure, Uniform, and Atomically Precise Carbon Nanostructures. So next slide, please. So I cannot end my talk without thanking all the people who did the real work. So I would like to thank all the previous students that I highlighted in yellow who did their experimental work and theoretical study. And I would like to thank Dr. Yasuto Masegawa, Hideto Ito, Larry Scott, and Mike Haley, who helped me co-supervising these students. And financial support is I would like to thank from JST Arauto, and I'll be happy to answer any question. Thank you very much.
Very nice talk, Ken. So we have some questions. The first is from Jorn Hansen. And Jorn is rather special because he was one of the first students that actually was in our center. And now he's an associate professor at the University of Tromsø in Norway. So this is the closest that we have managed to get this symposium to get to the North Pole. So his question is, very interesting curved nanosheets. What type of materials applications do you envision for your structures?
Yes, that's a good question. So one of the good things about three-dimensional curved nanographenes or analog is that high solubility and also achieving the three-dimensional pi stacking. So by using that, so that will help use our material as a printable materials, and also the later advantage will be able to use for transfer capabilities. So we're hoping that our material will have an impact as a universal transporting materials that can be used for organic EL or FET as well as a solar cell. So this is what we're trying to do now.
Okay, great. So the next question is from Chitani at Osaka University. How special is O-chloranil as the oxidant for a series of your reactions? Does O-chloranil play any role other than the oxidation of palladium-0 to palladium-2?
Yes, that's very, very important question. So orthochloranil is many cases is essential in our CH functionalization chemistry. And both two features are important. One is it has to be orthochloranil structure. And by doing so, we're thinking that the palladium is sitting between two oxygen for behaving as a redox active ligand on palladium. And the second issue is oxidation properties is also important. It has to have relatively high oxidant. So it has to be orthochloranil. Simple chloranil or T-butylchloranil, orthoquinone is not that great. Of course, the paraquinone is all not good. So this seems to be part of the answer.
Okay, and one more question from Kathy Covert at NSF. Ken, do these extended curved pi systems have any interesting electronic signatures, UV-Vis or others?
Oh, so for UV-Vis, as I already a little bit mentioned, yes. So it has a relatively wide homo-lumo gap compared with flat nanographene. So it fluoresces at the visible region. So this is some unique features of warp nanographenes.
Then a question from me, Ken. I mean, it's an incredible compounds that you've showed us. For characterization, would you have to rely on X-ray for everything, or can you get some information beyond requiring X-ray?
Yes, that's a very good question. For our first generation warp nanographene consisting of 80 carbons, we were able to confirm that by X-ray. But if you go for a bigger one, it becomes more and more difficult. And we're like seeing the limitation of the typical characterization method for small organic molecules. So what we're trying to do now is to take the solid phase properties like Ramans and many others, or spectroscopy, and then try to bridge the gap between small molecule and big materials. But this is not that easy, to be honest.
Okay. And then I have a message for you from Osaka, and I think we can all agree with this message, which is thank you, Itami-san, for a great talk.
Thank you very much.
Okay, well, this concludes the end of our session. We've obviously had 4 incredible talks covering very diverse aspects related to CH functionalization, from thinking about it as a strategic reaction, developing new synthetic methods, and developing predictive models from that. The wonderful talk by Ken Hauk on the various computational aspects of how to think about CH functionalization, and now the spectacular finish of applications towards material science. Some really unusual compounds without thinking about CH functionalization strategies would simply not be accessible. So we need to thank all of our speakers for doing such a great job. And also we need to thank the managing director of the center, Dan Morton, who has done a spectacular behind the scenes interactions with all the speakers and with many of the sites to make sure that this would flow smoothly. And I think, Dan, this is the one that's been most smoothly so far. So congratulations for an excellent job. So once again, thank you all for attending. I know you're coming from all different time zones, some of them not as social as others, but those in Europe should now be going out well, the bars have closed probably in Europe. Well, you should probably just be going home. And then, of course, I'm not sure what you should be doing in Asia at this time, but maybe it's even too early to start work. I don't know. But anyway, it's great to have you all coming from all over the world. So congratulations to the speakers, and thank you, everyone.